Hi everybody, this video is going to talk about the AP Physics review for the energy unit in the multiple choice section. The first question, I don't know what happened to number 1, I think I deleted it, so we're at number 2. A force F at an angle theta above the horizontal is used to pull a heavy suitcase of weight mg, a distance d, along level floor at constant velocity. The coefficient of friction between the floor and the suitcase is mu. The work done by the frictional force is what? So I have a diagram here. Here's my floor, here's my suitcase, here's my theta, and the force is along this line, this vector. So our formula for force is force that is parallel to the distance, but our force is not parallel to the distance here, and so we have to use the other part, which is FD cosine theta, and it is cosine because it's the force that is acting in the direction that it's moving, and so that is the cosine. So we need to start with that as a background just to get an idea of what's going on. That work that's being done, and the question is the work done by the frictional force is what? The work being done, it's keeping it at a constant velocity, and so this is the work that's being done. So that is A. It is negative because it's going in the opposite direction of the motion. So we know that the motion goes, like according to how I have drawn it, the motion would be going this way, and so therefore the frictional force acts in the other direction, and so that is the negative. Number 3, the force has to be parallel to the distance. So, if the force is moving this way and it's moving the object in that direction, then you're good. But in this case, it's going in a circle, and that is not parallel to the distance. So it's just 0. It's not parallel. Number 4, we went over together in class. I'm going to move over to another screen where I showed some of that work. So these are notes from class the other day, but what we talked about is that we need to find this distance, which we're calling the delta H. And so if we use our setup for change in gravitational energy, then we come up with this. And at that point, we're almost done because the question is asking for the change in potential energy. So the only thing we need to do now is plug in what is this distance. And this distance is L minus L cosine theta. And so if I factor out the capital L, then I get 1 minus cosine theta. And so this should be my answer, and if I look to my multiple choices, that is listed as answer A. Number 5, a softball player catches a ball, moving towards her with a horizontal speed of v. While bringing the ball to rest, her hand moved backward a distance of d. Assuming constant deceleration, the horizontal force exerted on the ball by the hand is what? Well, we have to think about what involves force. We know that work is force times distance. And we know that the ball is coming at her with a kinetic energy of 1/2 mv squared. So now we're really just going to be solving for force. So we're going to take this and solve for force. In other words, we're going to divide by d here. And so what we have, and now the 1/2, just remember that a 1/2, you can put it all in the numerator, but that doesn't really make sense. When we do it, we really split it up like this, like that's 1/2. And we have our mv squared on the numerator, and we have our distance on the denominator. And so if we look at our options, that is option A. Okay, the next question. A pendulum is pulled to one side and released. It swings freely to the opposite side and stops. Which of the following best represent the graphs as kinetic energy, potential energy, and total mechanical energy? So I'm going to start off by talking about total mechanical energy. So mechanical energy should be the same throughout. And you can see the line. This is the total mechanical energy line. And on this one, it's down here. Well, that doesn't make any sense. The total is all of it added together, so it can't be that. Next thing I'm going to talk about is potential energy. So that is, in this case, that's this line, or in this one, this line, and on this one, this line. Another thing that we know is we know that kinetic energy is 1/2 mv squared. Now I know we're talking about potential in this one, which is a different energy, but the kinetic energy has to be parabolic. It's not going to be A. Because the kinetic energy is parabolic, the potential is also parabolic. It's just the opposite. So now we just have to decide between these two. As we take a look at this, a pendulum is pulled to one side and released. So the start time is like up here. I'll use this diagram up here. The start time is right here. And then it's going to go through and go to the other side. So we're talking about the start. At the very beginning, the instant before it's released, remember it was in a stopped position, so it has no potential energy to start with. No kinetic energy to start with. That is, I'm going to go back to my highlighter here. The kinetic energy is this line. And when it starts, it has no kinetic energy. So that's why C is correct. It has no, when it starts over here. It's not moving, so it does not have kinetic energy. So C is the right answer. Okay, question 7 and 8. A car of mass M slides across a patch of ice with a speed V with its brakes locked. It hits the dry pavement and skids to a stop in a distance D. The coefficient of friction between the tires and the dry road is mu. If the car had a mass of 2 meters, it would have skidded how far? Okay, so we are basically looking at one of those instances, we've talked about this before, where you look at the equation and you see, okay, if this one doubles, what does the other one do? So I'm just going to back up and say, okay, the work done by friction should be equal to the kinetic energy. So it's skidding along the ice, and then it hits the dry pavement, and it slows down. And it slows down, and it comes to a stop eventually. So whatever work is done by the friction should equal the amount of energy that it had going in. So we're there. Sorry, we're up here. So we're here. So the work is equal to kinetic energy. That's what I have here. The force that we're talking about is the frictional force. And frictional force is mu times mass times gravity. So that's where I've come up with this. So now my mass can cancel out. And so the question is, how far would it skid if it had twice the mass? Well, the mass is irrelevant. The mass cancels out. And if the mass cancels out, then the mass does not affect how far it goes. It doesn't matter if it's, I don't know, a Mini Cooper or a semi-truck. It doesn't matter. It's going to go the same amount of distance under these situations. Number 8, if the car had a speed of 2v, how far would it skid? Let's go back and pick up where we left off. So we did this, and now what I've written up here is after I canceled out the mass. And we're looking at what if it had a 2v, what would have happened to the distance? So let me just solve this for d. So I'm going to divide both sides by mu times g. So that's going to give me distance is this, which I had before, divided by mu times g. Okay, so now let's focus our attention on the velocity. And if I double that velocity, what's going to happen to the distance? So in other words, now instead of v, I have a 2v over 2 mu g. And that's going to give me, I'm kind of out of space here, I'm going to come up here. That's going to give me a 4v squared over 2 mu g. So if I compare my 4v squared to what I had before, it's 4 times greater. So my distance is going to be 4 times greater. Okay, number 9, a ball thrown vertically upwards with this velocity v, kinetic energy ek. When it's halfway to the top of its flight, it has a velocity and kinetic energy of how much? All right, we know that in this situation, the gravitational energy is equal to the kinetic. So, you know, when it starts, just right before it starts, it doesn't have any kinetic energy, but it does have, when it leaves their hand, it does have kinetic energy, but it does not have gravitational. And then it gets up to the top, and now up here, it's got all potential, but no kinetic, because it stops for a second. And the question is, okay, well, what about halfway? Well, halfway, our height is going to be half the height. And so, if it's half the height, then it has half the energy. So the energy is going to be cut in half. And if the gravitational potential energy is cut in half, well, the kinetic must be also cut in half. For instance, let's say we started off with, in this case, it starts off, let's say, with 10 joules of kinetic energy. Well, halfway up, it's going to be half of that. So now the gravitational has gotten half bigger. So that means we're down to 5 over here because it's half. So the halfway point is going to be exactly half. So that's why we have this. So it's not this one. Then what about its velocity? So we look at the velocity. We've talked about this a little bit before, that we can solve this. The m's cancel. I can multiply by 2. Now I have a v squared over here. So in other words, v is equal to square root of 2gh. And that's an important little shortened formula to keep in your back pocket. So halfway to the top means that the height is halfway. So now we're up to v equals a square root of 2g times 1/2 h. Because now we're talking about halfway up. Okay, well, halfway up, if we compare these two quantities, then this one has a square root of 1/2 inside of it. So the difference is a square root of 1/2. That's the difference between this equation and this equation. Square root of 1/2 is right here. Because square root of 1/2 is like square root of 1 over square root of 2. Well, square root of 1 is just 1, so that's 1 over radical 2. Okay? So B is the answer here.